Algebra 2, Chapter 9.2, exercises 1 through 12. In this section, we're working on rational functions. And before going through these exercises, I'm going to explain what a standard form of a rational function is. First of all, there is the parent function, rational function listed above. Sometimes it's called the reciprocal function. This fx equals 1 over x. And also there's this one here, f of x equals a times 1 over x minus h plus k. Now, if you've been in my course so far this year, you've seen the h and k before, and you've also seen the a. So we're going to look at how eventually these items change the parent function, which is fx equals 1 over x. What a does is a will determines two things. It determines the vertical stretch or compression, we'll call that, of the parent function. Also, if a is less than 0, the function reflects about the x-axis. And if a is greater than 0, the function does not reflect. H reflects, translates, so H translates f of x, the parent function, left and right. And you might remember that if h is positive, the translation is to the right. If h is negative, the function translates to the left. And it's sort of counterintuitive. This k at the end, k translates f of x up and down. So we'll get into those as we go today. So describe, we're going to do the odd number problems here in this video lesson. Describe how the graph of g of x is related to the graph of fx equals 1 over x. Well, what we have here is, if we look over at our model at the right, we see the only thing that deviates from the parent function is this thing right over here, and this is the value of k. And since k is equal to 4, then g of x is f of x. I'll call it fx equals 1 over x translated four units up. And so you're just taking the standard parent function, translating it 4 units up. So the standard parent function looks like this, and just here it is, just like this. That's the standard parent function. What you're doing is you're taking this parent function and translating it 1, 2, 3, 4 units up, and likewise the bottom section 4 units up. And so the horizontal asymptote to this function becomes f of x, I'll just say y equals that becomes y equals 4. Let's go on to the next odd number problem 3. We have g of x equals 1 over x plus 3. Well, in this case, what we have is we have x plus 3 in the denominator, and in order for this function to be x plus 3, h has to equal -3. And if you look at the standard parent function that we talked about earlier here, if h is -3, then we'll have x minus -3 or x plus 3. And so what this means is that g of x is f of x equals 1 over x translated three units to the left. And this one here is somewhat counterintuitive, especially if you haven't worked out these kinds of translations before in any of the other things we've gone into. So that's what it's going to do for problem 3. We're going to go on to but before we go on to the next odd number problem, what I like to do for something like problem 4, where you have a coefficient in the denominator, what I like to do is make this like an a. So if you're dividing by 0.1, that's the same as multiplying by 10. And that's because if you have 1 divided by 1/10, if you divide by a fraction, it's the same as multiplying by its reciprocal. So we have 10. So before working on number 4, what I would do is I would make this into 10 times 1 over x. That could make your transformation life easier. Okay, next is odd number problem. We have 5. G of x equals 1 over x minus 7. Well, in this case, as in problem 1, we have k is equal to -7. So therefore, g of x is f of x equals 1 over x translated seven units down. Okay, that's number 5. Next, number 7. Okay, here we go. We have this negative 0.1. I'm going to write this out as a fraction, change this decimal to a fraction, because I think that's going to be a better easier to explain verbally what's going on here. So this negative 0.1 is the same as negative 1/10. And so it's going to be negative 1/10 times 1 over x. And so what this is we have a's being negative. So in this case, g of x is f of x equals 1 over x. This negative sign reflects, so I'll say reflected about the x-axis and what does that 1/10 do? And vertically compressed by a factor of 1/10. So that's going to be what number 7 does. Next, under problem, we're getting to the section here where we're given a graph of the parent function f of x equals 1 over x, and we're asked to, based on g of x equals whatever it is, to find out what the different parameters do to transform this graph of the parent function, and gives us 2 reference points to consider. These reference points, -1, -1 here in the third quadrant, and 1, 1 in quadrant 1. So let's go ahead and see what happens. We have our first example, first problem, g of x equals 3 times quantity 1 over x plus 1 minus 2. And what we're going to do is the center of the function is located at the coordinate pair h, comma k. And this function here, h, to get in the denominator x plus 1, h has to equal -1, and then k is going to be equal to -2. And so in this instance we have, for our center, the coordinate pair -1, comma, -2. And so what's going to happen is that is going to be where, that is going to describe our vertical and horizontal asymptotes. So we're going to have a vertical asymptote. For a vertical asymptote, we're going to have the equation x equals -1. And so I can go and draw this little dashed line down below. I want to put x is equal to -1 and label that that's going to be our vertical asymptote for this problem. And our horizontal asymptote, similarly, is going to be the equation y equals -2. So now I'm going to sketch that in, and here we go. So we have y equals -2. And what this is going to do is move these given reference points to the left 1 unit and down 2 units. So this -1 comma -1 is going to come to the left 1 and down 2 right here. And likewise, our 1 comma 1 is going to move left 1 and down 2. So I've just relocated these reference points. So we have over here, I'm going to draw an arrow of what happens here. This one here became 0 comma -1, and this one over here is going to be -2 comma -3. Okay, so now we have those located, and now we look at this 3. What does this do? This 3 vertically stretches by a factor of 3. So let's go ahead and see what happens. If we vertically stretch from where this would normally be, it's going to take this point here at 0 comma -1, and we're going to have to multiply by 3 from its distance from the horizontal asymptote. So that's times 1 times 2 times 3. So that's where this is going to be, what I'm arrowing to right now. That's going to be the point, coordinate pair of 0 comma 3, and below the horizontal asymptote of y equals -2, that one is going to be vertically stretched by a factor of 3 also. So I make that point here, and that's going to be the point -2 comma, and that's going to be -5. So let's go ahead and summarize what happened to these reference points. We have -1 comma -1 transforms, we'll call it transforms, to this -2 comma -5. And then the other coordinate pair, 1 comma 1, transforms to, we have 0 comma 1. So that's going to be what happens to those 2 reference points. Okay, there's number 10, and again for number 10, what I would do for this one is I take that -0.5 in the denominator, and I would make that -2. So you'll have, that'll become -2 when you move it out of the denominator, times 1 over x minus 3, and then bring this plus 1 here. Anyway, recommendation, that could make your life easier. Okay, here number 11 is the last one we're going to do in this exercise set. I'm going to take that decimal again, as I've done before, and turn that into a fractional form. So I'll make that -1/2 times this 1 over x minus 1 minus 2. Now in this case, our h comma k is going to be h is equal to 1 and k is equal to negative 2. And so this describes where our vertical and horizontal asymptotes are going to be. And so that creates the center for this version of the transformed rational function. So again, as I've done before, problem 9, I'm going to take this we'll say our horizontal asymptote is going to be the function y equals negative 2, and our horizontal asymptote is going to, our vertical asymptote is going to be the equation, notice I didn't say function, x equals 1. So that's going to be our vertical asymptote, and our y equals negative 2 is going to be our horizontal asymptote. And what that is going to do is going to take our coordinate pairs, our reference points, and this negative 1 comma negative 1, we're going to move 1 to the right and down 2 like this. So this is going to be changed to be 0 comma negative 3. And then similarly, we're going to have our 1 comma 1 reference point, move that to the right and down 2. So this is now going to be the coordinate pair 2 comma negative 1. Now, doing this and just looking at this reminds me that I've neglected to sketch in the graph on problem 9, because I think that's one of the things. Oh yeah, and other things. State the domain and range using inequality, set notation, interval notation. Yeah, so let's go ahead and finish up number 9, really. So we've changed, this becomes, I want to get this right, so that's 1 up. This is the point here, and we're going to go through this point too. So the thing is going to come like this. So that's the curve in quadrant 1, or not quadrant 1, but to the upper right of our center. And then this one here, we're going to have just like this. So that's the curve, vertically stretched by a factor of 3. Okay, next says domain. Well, our domain, we have interval, we have in inequality notation, we're going to have x is less than our vertical asymptote, negative 1, and also x is greater than negative 1. In set notation, we're going to have make this bracket, x is an element of all real numbers, but x, except x cannot equal negative 1. And finally, in interval notation, we have x is greater than negative infinity, less than -1, union greater than -1, less than infinity. And our range is going to be a similar type of notation. We're going to have y is greater than -2, and we're going to have y is less than -2. We're going to have, in our set notation, y is an element of all real numbers, this double script r, except y cannot equal -2. And then finally, in interval notation, we have greater than -infinity up till less than -2, union greater than -2 to less than infinity. Okay, now I think we have everything. Okay, back to number 11. Okay, we've already transformed these reference points, and I've already marked what they are. Now we're going to look at this -1/2. What this -1/2 is going to do is I'm going to reflect first about the horizontal asymptote. So here, this coordinate pair will come up here, and this one that was 1, 1 is going to come down here. And is going to be vertically compressed by a factor of 1/2. And so now that'll come here like this, because the distance between the horizontal asymptote and that reflected reference point is 1, so half of it is right there. So, and similarly for this other one that we reflected becomes this. So now what we have, it might be kind of hard to see here, this one here becomes 0, comma, looks like -1.5, 0, comma, -1.5, or -3/2. And this other one here that I'm pointing to becomes 2, comma, that's going to be -2.5, 2, comma, -2.5, or -5/2. So I'll state it this way. I'll say this -1, comma, -1 transforms to become the coordinate pair 0, comma, -3/2, and the other coordinate pair or reference point 1, 1 transforms to become the coordinate pair 2, comma, -5/2. Okay, so now let's go ahead and see what the graph of this looks like. What we've done is, on the right side of the vertical asymptote, that's going to look something like this. And on the left side of the vertical asymptote, we have this thing right here, and it's going to come like this. And what I did, well, I'm going to show that. Yeah, I guess I'll show that right now. What I did is I went to my TI 84 CE calculator and put in this version here. I put in the numerator negative 0.5 over x minus 1 minus 2, and this is what it looks like. We have our horizontal asymptote, y equals negative 2, our vertical asymptote, y equals 1. We have our reference points that we moved were 0, comma, negative 3 over 2, and then 2, comma, negative 5 over 2. So that's where they went. Now, next, we have our domain and range. So we have domain. We're going to have x is less than our vertical asymptote, so less than 1, and x is greater than 1. We have in set notation x is an element of all real numbers, but x cannot equal 1. And then finally, for our interval notation, we have greater than negative infinity, comma 1, union negative infinity, comma 1, union 1, comma infinity. And for our range, that's going to be a similar notation. We're going to have y is greater than negative 2, and we're going to have y is less than negative 2. Again, that's going to be the location of that horizontal asymptote. We're going to have in set notation we're going to have y is an element of all real numbers, but y cannot equal negative 2. And finally, for interval notation, we have greater than negative 2 up to, but not including, negative 2, union negative 2, comma, infinity. And so that's going to be all of it here. But let's take a look at just number 12. I'm not going to actually work out number 12, but here we have 2 in the denominator. So this can be rewritten as 1/2 times quantity 1 over x plus 2 plus 3. So we can do similarly. We did. So I hope this has been helpful to you. Good luck, and as always, thanks for viewing.